Hello, everybody, and welcome to our next video in Unit 6, which is all about calorimetry. You might be familiar with calorimetry to start off with. Sometimes in Chem 2, I focus a lot on calorimetry. Other times, I'll focus a little bit more on solutions like colligative properties. So either way, I think I try to always touch on calorimetry at least a little bit in Chem 2. So some of this, the equations for this should be pretty familiar. Actually, you might remember the equation before I even get started here, because we do a very nice calorimetry lab in Chem 2. But anyway, how do chemists measure the heat transfer between two substances? So how do they do that? Well, there's two ways that it can be done, but the overall technique is what we know as calorimetry. So calorimetry is a technique used to measure heat flow in a chemical reaction. And it's based on observing the temperature change. And remember, a temperature change we can denote, it's symbolized as delta T. So let me get a delta here. Just a little triangle, delta T. And a reaction absorbs or releases heat. Actually quite a simple process, calorimetry. And the way that we've done it in Chem 2 is by using a coffee cup calorimeter. And we call this a simple calorimeter. Oops, looks like my other picture is on the other page. So let me go up here a little bit. There we go. Wonderful. So here's a coffee cup calorimeter, AKA a simple calorimeter. These simple calorimeters are very cheap, but they're actually quite effective. They do a really nice job of measuring heat flow. And that's because you tend to do this in a styrofoam cup. And styrofoam cups are very good insulators of heat. So you won't lose or you won't absorb heat from the surroundings being your hand. Instead, if it does absorb heat, it tends to do that with some water on the inside. So you might remember doing this from Chem 2, but I like to usually use 2 cups just for extra installation. And you have a thermometer that's in here. And inside, you have some water, okay? And then you put your sample inside. So this would be an example of some sample, whatever it may be. And that sample is going to do whatever it does. If you're measuring thermal equilibrium, it might not react, but you can measure the temperature change of the water. Or if it is dissociating, you can measure the energy change from that particular from that dissociation. So in the previous video, we looked at heat of solution. So you can measure heat of solution that way as well. This thermometer is going to measure the temperature change. So this could either increase in temperature or it could decrease in temperature. And that temperature change tells us a lot about the heat change in that solution as well. And coffee cup calorimeters are quite useful for when we use solids, when we use liquids, or when we use solutions. Now, are these good for like actual chemists that are measuring things? No, right? They have much more advanced calorimeters that are a lot more money. But in a high school chemistry course, coffee cups do a great job. And we're never going to use gases in either of these examples. But if you were to use a gas in a reaction, you would use a bomb calorimeter. And a bomb calorimeter is a lot of money. The last time I checked, these were about $32,000 per bomb calorimeter. And these bomb calorimeters, what they do is these tend to measure the heats of reaction with gases. So a lot of times this will measure the amount of energy that's involved in combustion reactions. So combustion, of course, is some reaction with oxygen gas. So you would input some oxygen gas into this chamber, and the reaction would occur in this little chamber on the inside. This whole system is going to change temperature. And we can measure the temperature change by taking the temperature of the water on the outside. I did use a bomb calorimeter once when I was in undergrad. They're actually quite small. They're a lot smaller than you would think. And from what I remember, it did a good job. But there was only one bomb calorimeter. So, and that was in one of the highest level chemistry classes I ever took, one of my least favorite, actually, because I'm not good at calculus. But yeah, we measured the amount of energy, I think, in maybe in a peanut. I don't remember. But it's pretty cool. And they could use bomb calorimeters to determine actually how many calories are in certain foods. So let's go ahead and not talk about the processes anymore, but what can we use with that information? So I mentioned this briefly in the previous video, but let's get down the definition for specific heat capacity. So the specific heat capacity, you might remember talking about this in Chem 2 as well, is the amount of heat needed to raise 1 gram of a substance by 1 degree Celsius. We actually did talk about this in the last video. I only know this because I just filmed that last video 2 minutes ago. By 1 degree Celsius. So, depending on the substance itself, the nature of that substance, or the type of bonds it has, the specific heat capacity will be a little bit different. And the specific heat capacity, it's always symbolized by a lowercase c. So it's a lowercase c. And if I look at table 1 below, the specific heat capacity is different for basically everything. Water, liquid water, has 4.184. A lot of times you might see another sig fig tacked onto there. That means that we have to input 4.184 joules of energy to raise 1 gram of water by 1 degree Celsius. Let's look at, ice right here. Ice, we have to input 2.06 joules of energy to raise 1 gram of ice by 1 degree Celsius. Okay, so a little bit less energy for ice cubes. And there's some values here for all these different types of molecular substances. So these are all molecular. And we know that because they're comprised of all nonmetals. As I go down, other than carbon, these are all metallic in nature. So all of these have metallic bonds. And notice how small these specific heat capacities are. Wow, look at gold. Gold, 0.129 joules of energy is required to raise 1 gram of gold by 1 degree Celsius. That's a lot less than water. The reason why has to do with those metallic bonds and those delocalized electrons. Because those electrons can move so much more freely, heat can move within a metal much more readily than it can for molecular solids. This is why we know of metals having that they're very good conductors of heat. It has to do with that sea of electrons, and we could see here quantitatively that it requires a lot less energy to raise 1 gram of a metal by 1 degree Celsius. Anyway, we can measure the amount of heat. Heat is typically denoted by the variable Q, a lowercase q. And the amount of heat that's required or absorbed is equal to the mass of that substance times its specific heat times its delta T, its change in temperature. And your change in temperature is going to be the final temperature minus the initial temperature. That's important as we progress through these here. Rather than talk more about this, let's go and do some examples here. Another thing I want to mention, though, is that specific heat capacity tends to be in joules per gram degree Celsius. You might also see a molar heat capacity. And it's the same exact thing. Your molar heat capacity would be joules per mole degree Celsius. Be careful with those, okay? Moles versus grams, it's a simple molar mass conversion between those two. Let's do an example here. Calculate the heat absorbed when 100 grams of copper, or by 100 grams, when the temperature is changed from 22 to 100. The specific heat of solid copper is 0.384 joules per gram degree Celsius. We're just going to use a good Q equals MC delta T. This is the big equation you should know for this unit. So I want to calculate Q, the heat, Mass of the sample is 100 grams. Specific heat is 0.384 joules per gram degrees Celsius. And my delta T. Delta T is always measured in final minus initial. So the final temperature was 100 gram or 100 degrees Celsius, and my initial is 22. So my Q in this case should be 3.03. Oh no, just 3.0, excuse me. Let's make a little mistake here. Times 10 to the third joules. Units for heat are just joules, because if I notice, here's grams in the numerator and grams in the denominator, degrees Celsius in the numerator, degrees Celsius in the denominator. So I'm left with just units of joules. I did have to input energy, so this is a positive value for Q, and that's because the temperature changed from 22 to 100. So in order to raise the temperature, I had to input heat energy. So it makes sense that Q is positive in this example. I had to put energy into this. These sort of equations are very simple, okay? Just a basic calculate the heat in order to raise the temperature of something, or when something loses some heat. However, we could get a little bit more specific here. And it's very important for us to remember that heat lost is equal to heat gained. This is huge right here. Heat lost equals heat gained. When we do calorimetry, okay, so a lot of times if I go back to this coffee cup calorimeter, we have water and we have a sample that's inside the water. This water is going to change temperature because this sample that's put in is either giving energy to the water or it's absorbing energy from the water. The amount of energy that this absorbed or released is equal to the amount of energy that the water absorbed or released. So if I can measure the temperature change of the water, that can tell us a lot about the substance itself, because the heat lost is equal to the heat gained. So if I have a hot metal and I place a hot metal into a big beaker of cold water, this particular sample, this heat or this hot block is going to transfer energy to the water. So this hot metal is going to be less hot, whereas this water is going to become cool. However, there is a point at which a thermal equilibrium is reached. And a thermal equilibrium is when the two substances end up at the same temperature, okay? So if we think equilibrium, it's when when the rate is the same in both directions. The amount of heat that this hot metal or this warm metal is giving to the water is equal to the energy that this water is giving back to the metal. It is the same amount of energy. When I put this hot metal in, this is not at equilibrium because all of this energy is going to the water. It's at equilibrium when the energy is the same in both directions. So let's take a look at sample problem 8. A copper cylinder has a mass of 76.8 grams and a specific heat of 0.092 calories per gram degrees Celsius. Calories is just another unit for heat. It's heated to 86.5 degrees Celsius and then put in a 68.7 gram turpentine whose temperature is 19.5. The final temperature of the mixture is 31.9. What is the specific heat of the turpentine? So let's try to draw a picture here because it might be a little bit easier to consider this. Copper cylinder has a mass. So I have some piece of copper right here. And I heat this to 86.5 degrees Celsius. And this has a mass of 76.8 grams. I'm putting this into turpentine. So this is the turpentine. I'll just put terp down here. And this turpentine has a temperature of 19.5. When they reach thermal equilibrium, the final temperature of the mixture is 31.9. So we want to know what's the specific heat of the turpentine. What we can do first is let's figure out how much energy the copper lost. Okay, so I know a lot more information for the copper than I do the turpentine. So I could use Q equals MC delta T here. If I want to know how much heat the piece of copper lost, okay, that Q is equal to the mass of the copper, which is 76.8 grams, times the specific heat of the copper, calories per joule, I keep saying joules, grams degrees Celsius, times delta T. So the final temperature is 31.9 minus the initial temperature of the copper. The initial temperature of the copper was 86.5. And I find that your copper would have released 390 calories of energy. Okay? Copper released 390 calories of energy. If the copper released 390 calories of energy, that must mean that the turpentine must have absorbed 390 calories. So Q is equal to positive 390 calories in my turpentine example. The energy went from the copper to the turpentine. The turpentine absorbed that energy. Because if I notice, the turpentine raised temperature, it was 19.5 and it went to 31.9. Knowing that, I have the mass of the turpentine is 68.7. Specific heat's what I'm trying to find, times my delta T. So final minus initial again, 31.9 degrees. The final's the same. Notice that. Minus the initial temperature of the turpentine was 19.5. And when you solve for this, you should find that the specific heat for turpentine is 0.45 calories per gram degrees Celsius. Let me highlight something for you. This right here and this right here is what you need to know. The heat that's lost by one object is equal to the heat that's gained by the other object. So they are the same absolute value, but those signs are changing. Okay? That's what we have to take away from this. Heat lost equals heat gained. That's huge. Let's highlight this up here as well. That's how important it is. Okay, heat lost equals heat gained. And notice how these ended up at the same temperature at the end. And like I mentioned previously, we call this thermal equilibrium. So let's get a definition for thermal equilibrium. This is when two substances in physical contact with one another exchange heat energy. So, say I have two blocks right here. Block A has a higher temperature than block B. At first, they're not touching one another, but we'll see that when they are in contact with one another, the energy from your hot block goes to the energy of the cooler block. So it's transferred from warm to cool. And at some point, they're going to reach the same temperature. Now remember, this is not at equilibrium, this middle one, because all of the heat energy is going in one direction. These are at equilibrium because when they are the same temperature, the heat that's going from A to B is equal to the heat that's going from B to A. This right here is considered the thermal equilibrium. So we've talked about equilibrium already. So it makes sense that it's the same in both directions, right? The same rate, same amount going in both directions. So let's say, we're just going to call this the hot block. We could do this with water too, but we're just going to relate it to this example, the cold block. The hot block is releasing some energy, it's losing heat. So this right here is giving energy to this. So its Q is negative. However, this is absorbing that energy. So that has to be absorbing a positive value. So notice how I have positive Q and negative Q. But because it's going from A to B, And if no energy is lost, Q must be equal to Q for both of these examples. The heat that this lost is equal to the heat that this gained. So what we can do is manipulate these equations. I'm going to change this whole entire side so it's a negative, because negative Q equals MC delta T. In order to get these to equal each other, I'm going to say Q is equal to negative MC delta T. And we'll see that we can, I'm going to put parentheses around this because I think that's really important. Sorry to interrupt. But we can instead use negative MC delta T equals positive MC delta T. Okay, and this will allow for us to determine thermal equilibrium. This is only true when two substances end up at the same final temperature. Okay, let's take a look at this problem right here. So 50 grams of aluminum at 85 degrees was placed in 100 grams of water at 25 degrees. What happens to the temperature and the average kinetic energy of the aluminum? So you have this hot aluminum is placed into about room temperature water. Okay, should be very easy what's happening. Well, the temperature is going down. Temperature decreases. And if the temperature decreases, this also means that the kinetic energy must also be decreasing. And this is for the aluminum. Okay, if it was asking for the water, we would say the temperature and the kinetic energy is both increasing. Now, for thermal equilibrium, it does depend on the amount of substance. So if I have hot water and I have cold water, 75 degrees and 25 degrees, if I have the same amount of both of those, the thermal equilibrium would be 50. Right? That makes sense because there's equal amounts of hot water and cold water. However, it's not as easy if I have a lot more hot water, like I do in this example, and a little bit of cold water, or if I have a little bit of hot water and a lot of cold water. Thermal equilibrium is not as easy to calculate because it depends on how much of each type of water you have. Okay? When I make Natalie's bath, a lot of times I'll make it too hot or too cold. Let's say I made it too hot one day, okay? If I add a little bit of cold water, the temperature is not changing that much, right? So typically I'll have to let some hot water out of the bath and then add some cold water so the temperature changes a little bit more. So your thermal equilibrium in this case would be greater than 50 degrees. And that's because there's more hot water than there is cool water. If I have more cold water than hot water, your temperature would be less than 50 degrees. Okay, so it not only has to do with the samples themselves, but it also has to do with the amount of each of them. Let's do one more sample problem together. So a 65-gram piece of iron at 525 degrees is put into 635 grams of water at negative 15, or at 15, I'm sorry, positive 15. What is the temperature when the system reaches thermal equilibrium? Okay, so what we're going to do is consider what's losing heat and what is gaining heat. Okay, so key piece of information is missing. Let's see. The specific heat for iron. So iron specific heat is 0.449 joules per gram degree Celsius. So it looks like this iron is at a very hot temperature. So the iron is hot. This must mean that this is losing energy. It has a negative value for Q. So your iron is hot. Whereas your water is going to be cold or cool, doesn't matter. But your value for Q is going to be positive because that hot metal is going into the room temperature water. The value for Q is the same. So rather than doing two separate equations, let's just go ahead and set up one long equation to solve for this. This type of problem is very useful when you're not necessarily given all of the values, which we'll do some examples of this in class. So we want to get Q to be the same on both sides. So I'm going to do positive Q is equal to negative MC delta T here. So negative MC delta T, this is for the metal, so we'll do Fe, is equal to MC delta T for the water. I like to label which side is which because then I tend to lose track of stuff. So I will always label which side is which so I remember. Parentheses is important around this negative sign here. Let's just fill in my values. So negative mass of iron is 65 grams times the specific heat, which I forgot to give you, but it's up there now, joules per gram degree Celsius, times delta T. So your final temperature, oh, I'm trying to find the final. So TF minus the initial temperature is 525. If we want, we can do little parentheses around each of these. There we go. And that's equal to the mass of the water is 635 grams. Specific heat for liquid water is 4.184. And again, I'm trying to find the final temperature of the water. So I'm going to subtract from that the initial temperature of the water, which is 15. Hardest thing about these is the math. Okay. I'm not going to walk you through the math in this video just for the sake of saving some time. We will do some examples with this in class. I would work through this right now, see if you get the right answer. I tend to take my time. You do have to do a little bit of distributing because you have a TF in there. But if you do this correctly, you should find that your final temperature is 20.6. I'll walk you through the math in class. And that makes sense. I have a heck of a lot more water than I have the metal, right? So my temperature should be closer to 15. Also, the specific heat for water is much higher. I have a higher specific heat. In order for water to change temperature, I have to input a heck of a lot more heat than I do for this metal to lose heat, okay? So a couple of factors to keep in mind when we're considering thermal equilibrium is not just the amount, but also the specific heat of each of those. For the water, it didn't matter because specific heat was the same. But when we consider a metal into water or two different substances into one another, specific heat also plays a role. We will practice with this a lot in class. We did do this a lot in Chem 2 if I focused a lot on Chem 2 in that case, but otherwise, this is the primary stuff you need to know for this unit is Q equals MC delta T. As always, if you have any questions, let me know. We will do some practice in class. Otherwise, I will see you in the next video, which we will take a look at energy of phase changes. So I will see you then. Bye.